Good evening. Thank you so much for coming to this really important evening. I'm Tim Marshall, the Provost of the New School, and I'm delighted to welcome you here and thank you for coming for this keynote session of the 38th Social Research Conference, Unknowability. How do we know what cannot be known? So this conference is organized by the Center for Public Scholarship under the direction of Dr. Arian Mack, who's the Alfred and Manette Marrow Professor of Psychology. Arian is also the editor of Social Research, an international quarterly, and director of the relatively newly founded New University in Exile Consortium. For those of you joining the conference for the first time, this conference series actually began in 1988. And since 2010, it has been organized under the auspices of the Center for Public Scholarship, which is intended to be an intellectual crossroads for academics, students, the public, and policymakers, bringing the best scholarship to bear on critical and contested issues, which is, of course, a mission rooted in the founding history and ideals of the New School. So tonight, it is my very great pleasure to introduce our keynote speaker, John Barrow, who is Professor of Mathematical Sciences at Cambridge University and Director of the Millennium Mathematics Project, a program to improve the appreciation of mathematics and its applications, especially among young people and the public. His research interests are cosmology, astrophysics, and gravitation. Dr. Barrow has received many awards, and that's really an understatement, including the 2006 Templeton Prize, the Royal Society's 2008 Faraday Prize, the 2012 Zeeman Medal of the London Mathematical Society, the 2009 Kelvin Medal, the 2015 Dirac Gold Medal of the Institute of Physics, and the 2016 Gold Medal of the Royal Astronomical Society. He is a Fellow of the Royal Society and of the Academia Europaea. He has written more than 530 scientific papers and 22 books, which have been translated into 28 languages, including Impossibility, The Limits of Science, and The Science of Limits. His play, Infinities, directed by Luca Ronconi, won the Premi Ubu for Best Play in the Italian Theatre in 2002 and the 2003 Ital Gas Prize. And finally, he was the Gresham Professor of Astronomy from 2003 to 2007 and the Gresham Professor of Geometry from 2008 to 2011 at Gresham College. Now, just before John joins us, we have to make a small change in the program. So what is listed in the program is that following we're changing what is listed in the program, which is that following Dr. Barrow's talk tonight, Nicholas Humphrey will lead a short discussion and then field questions from the audience for John Barrow. Now, Dr. Humphrey is a senior member of Darwin College at Cambridge University, Emeritus Professor of Psychology at the London School of Economics, and very happily, a former Professor of Psychology at the New School for Social Research. He is a theoretical psychologist, internationally known for his work on the evolution of human intelligence and consciousness. He has studied mountain gorillas with Dian Fossey in Rwanda, was the first to demonstrate the existence of blind sight after brain damage in monkeys, proposed the now celebrated theory of the social function of intellect, and is the only scientist ever to edit the literary journal Granta. His books include Consciousness Regained, The Inner Eye, A History of the Mind, Leaps of Faith, The Mind Made Flesh, Seeing Red, A Study of Consciousness, and Soul Dust. And he's been the recipient of several honors, including the Martin Luther King Memorial Prize, the Pufendorf Medal, and the Mind and Brain Prize. So now it is my very great pleasure to hand the mic over to John Barrow. Thank you, John.
Thank you very much, Provost, and thank you, Ariane, for your kind invitation to come and talk to you as a sort of rather outlier in this social science conference. The subject of the conference and my talk is the unknown. This is, of course, a vast, untapped field, rather like studying everything that is not a banana. And what I'm going to do in my talk is to cover a number of different topics from different areas of mathematics and science, and even some social science, and even some in sports, which illustrate some of the problems of unknowability in mathematical sciences. All my examples will probably have some mathematical aspect, but don't be afraid. Remember what John von Neumann said: if people do not think that mathematics is simple, it is only because they don't realize how complicated life is. Well, the first sobering thought is that science is only possible because there are limits. Limits equals impossibilities. Things that you can't know, things that you can't do, things that you can't see. So there are things that we call conservation laws of nature, which are based upon symmetries. And these define what is and what is not possible in the universe. We believe there are a relatively small number of laws of nature, and therefore of symmetries that demand them. And there may, according to some string theorists, perhaps be just a single law of nature, although the reality is no doubt not quite as simple. But an important thing to recognize is that if you look at the universe at the level of laws, then it is indeed rather simple. There are a small number of laws and they're highly symmetrical. But the outcomes of those laws do not possess the same symmetries as the laws themselves, and their number is unlimited, and they tend to be asymmetrical and complicated and very, very difficult to understand. So if you look at the universe at the level of the outcomes of the laws of nature, like everybody who is not a particle physicist or a cosmologist, then for you the world is horribly complicated and higgledy-piggledy. It's only if you stop a string theorist or a cosmologist in the street and ask them if they think the world is simple or complicated that they'll try to persuade you that the world is really simple. It's because for them the world is most vividly expressed at the level of the laws of nature, where it is indeed apparently far simpler than we might ever have expected. Well, in finding that there are limits to what we can do and see and know, we've also appreciated that in gathering information about the world, in processing information, in determining what we can know, we have to do work, we have to expend energy. When this computer does things for you, you notice it gets hot. It does work, it generates entropy, the processing of information, the transfer of one list of numbers into another list, that's all any computation can ever do, requires work and it requires energy. And so binds it up with the laws of physics and the limitations that exist from conservation laws and other aspects of physics. Well, let's start our story. We should start with our patron saint, the Prince of Darkness himself, good old Donald. As we've already had introduced to us in the earlier discussion, he told us about known unknowns and unknown unknowns, quoting from sources in the past. But the bad news for him is that there are also unknowable unknowns, as the map makers of the 16th century were really cognizant of. So the understanding of the limits of science, the idea that there might be things that you could never know, gained some momentum in the 19th century with this gentleman, Emil Dubois Raymond, head of the Prussian Academy, I think, for a period, who gave a series of talks starting in 1890 about the limits of science, or things that we could never know. And the first of these talks he gave was a centenary, a celebration of Leibniz. And you remember Leibniz thought about making a machine or making an operation which would be able to answer all the questions that you fed into it. So he fondly imagined that all the dilemmas of theology and philosophy and Brexit and the Mexican wall, you would just feed them into this machine, turn the handle, and the answer would come out. It's a sort of oracle. There are other people other than Delphi that have had oracles in the past, and they tend to be bound up very much with your philosophy of what randomness is. And in many cultures, randomness is the voice, the mouthpiece of the gods. So if you want to consult the gods, you throw a die or you draw a lot, and that's how you discover the voice of the oracle. Well, I mention this simply because the examples that he picks with this slogan, "We don't know and we won't know," which was somewhat against the mainstream of thinking at the time, and in the 2 decades later when Hilbert was proposing 23 great problems of mathematics, he thought there were no insoluble problems of mathematics. Auguste Comte thought there were no insoluble problems. All problems were soluble. But what did he list? And I think for 1880, he's really quite prescient. He has 4 preliminary problems: the origin of life, the origin of language, the origin of human reason, and the evolutionary adaptiveness of organisms. So this is after sort of Darwin. So these he just thought were most unlikely to ever be solved. There was some chance. He couldn't see any point of principle which would stop you, except perhaps for the human reason. But the second group, he thought that these were of a fundamentally different sort, that these could not be solved in principle by human beings. Number 5, the origin of the natural forces and nature of matter, sort of thing that goes on at CERN and elsewhere, he just thought we would never be able to look on small enough scales and large enough scales to find all the ingredients that constitute the problem. And he may well be right. Number 6, he called it the sensation of qualities. I think what people call qualia today. You know, does the concept of redness mean the same thing to you as what it means to me? And how would we ever know? So, and finally, the problem of free will. So he thought these last 2, there was a fundamental problem of principle, just imposing the problem, let alone solving it. So this is how people, or at least one person who was rather influential, thought around 1880 and lined up examples of problems that might be insoluble. If we move forward to today, we could pick on 4 types of limit, which I will touch on. Things that you might call practical. So the problem of being able to discern the smallest ingredients of matter and the largest scale structures of the universe that might exist on a scale bigger than the visible universe. And there are problems of cost. There are problems of what we'll call chaos in a minute, and of complexity and tractability at understanding and predicting and explaining certain sorts of behavior. And there are practical limits on information processing. So how big you can build a computer that's not going to melt, how fast it can compute. There are cognitive limits, no doubt associated with the very structure of our minds and where they've come from, the evolutionary pressures that they have responded to. And this means our language, the concepts that we like, the sort of pieces of mental arithmetic that we can do, the things that we build up step by step to understand complicated things are reflections of our sort of cognitive spectrum, the things that we can imagine. There are some intrinsic limits that we see are rather profound, that contrary to what you might have expected, there are things that you can't show to be true or false using laws of logic or arithmetic. There are things that you can't compute. There are measurements that you can't make to arbitrary accuracy. And that's nothing to do with practicality. It's part of the fundamental makeup of the universe. There is a speed limit in the universe that has profound implications for what we can know about its structure. Signals, whether light or other forms of electromagnetism, can't propagate faster than the speed of light. And that places all sorts of unusual cosmological limits, I'll call them, on what we can and can't ever expect to know about the structure of the universe. Let's pick on a famous limit first, Heisenberg's uncertainty principle, a quantum limit. So everybody knows something about this, and from some popular books and articles, you perhaps have a naive view that this is telling you something along the lines of there's a limit to how accurately you can know something, how it's positioned and how it's moving, because when you try to measure where it is, you necessarily move it or perturb it in some way. This is a helpful first guide, the sort of thing that perhaps you would tell high school children as a first step, but it's not really the essence of this idea. So the fact that an uncertainty in your measurement of position of something and of its momentum, its motion, is bounded below by a new constant of nature, Planck's constant divided by 2 pi, could more accurately be interpreted as that there is a fundamental limit on the extent to which the classical concepts of position and momentum can coexist. So when you are down in the quantum realm of the very small, these classical concepts become rather blurred and sort of melt away. And they can't simultaneously coexist sharply with a precision that's better than that. This type of new quantum reality, this new picture of quantum reality, lies at the basis of some things that we've heard mentioned in passing, of perhaps quantum computation, quantum encryption, that would be unbreakable in principle, not just in practice. But you don't have to be exotic to be indeterminate. I kept wondering whether to include this slide, but I had a sort of personal liking for it because I realized only many years later that when I was a high school student and went to an interview to a physics department to see whether they're going to make me an offer of a place, that they asked me this question. I mean, I didn't know it was this question, and it was a slightly nasty question to ask. But if we imagine an idealized situation, you know, like the massless pulleys and frictionless surfaces you meet in school textbooks, but this is a perfectly rigid beam, and imagine it's resting on 2 perfectly rigid supports at A, and it has a weight W. Forget about B for the moment. And you ask, well, what's the force that acts on A and A, because it's not twisting there the same? Well, the weight is W, so twice A must equal W. So I think I was asked something like that. It's a rather easy question. But then the lecturer interviewing said, well, I'm now going to, I mean, he had one of these bouncing on his finger, and he got his colleague to put his finger under the middle to support the middle as well, just. And he said, what's the force on the 3 supports now? So you look at it one way, why should anything change? You know, if there's half W here and half W there and nothing here, it's perfectly good. But there could be a third W here and a third W here and a third W there. In fact, this is an indeterminate problem of very simple statics. All you can say is that twice the force of A plus the force of B is equal to W. So there are an infinite number of solutions of this problem. It is indeterminate, even though it's the simplest static engineering problem you could ever conceive. So ordinary mechanics cannot give you an answer. If you give up the idealization and be realistic and allow the beam to flex, then there is a unique solution. And A is 3/16 of W and B is 10/16. So even at the level of very simple statics that you might meet when you're about 12, 13 years old in high school in England, there is a fundamental indeterminism that you can't get around if you have an idealized problem. The next type of barrier to complete understanding is something that's become known as chaos. I think this name was invented in the mid-1970s at Berkeley by Oscar Langford. But the concept was recognized, revealed, publicized by James Clerk Maxwell, a great British physicist, greatest after Newton, who unveiled the theory of electromagnetism. And he gave a sort of evening talk, which was supposed to be on free will. He was asked to give a talk about evolution and free will. And people were expecting he was going to reconcile somehow how free will could coexist with something that appeared deterministic, like evolution by natural selection. But what he talked about was completely different. He started by saying, well, people lay great stress on Newton's laws of nature as being deterministic. But the reality is that in practice, they're not. And he gave a nice Victorian example. He said, imagine you have a railway line here, and here is a point where you deviate away. And I've made the destinations Cambridge and Oxford. So one is going sort of tonight, and the other is going today. And you'll have a little lever here, and a tiny change of this lever produces a huge deviation in the eventual destination of the train. So this is his example of how a very small change can have a very large consequence, that a small amount of ignorance can produce a huge amount of ignorance. And this is a good definition of chaos. It's simply dramatic sensitivity to ignorance. And I think in one of the science sections to come in the conference, we're going to hear from people who work in study of climate science, where the paradigm situation of chaos exists, predicting the weather in the short term, in the medium term, in the long term. Why is it difficult? It's not that there's some unknown law of weather that we don't know, but we don't know the state of the weather everywhere now with sufficient accuracy to overcome this sensitivity. Weather stations every 50 or 100 miles over the land or sea allows for sufficiently different extrapolations and interpolations in between them to produce rather different forecasts for some aspects of the weather even tomorrow. So there is a practical limitation, and Maxwell points out that this renders impossible the prediction of future events with the precision that the sort of Newtonian philosophers always seem to assume about the deterministic world. Here's a simple example. So suppose we have a universe that has one law in it, and this universe is a circle, and just to show how classically educated we are, we'll call this angle theta. So the angle from 12 o'clock to this point here is theta, and the one law in this universe changes theta to 2 theta. So if you start at 30 degrees, it moves it to 60, to 120, to 240, and it goes round and round and round. This universe is completely deterministic in principle. If you know the initial point of that pointer after any number of applications of the law, you will also know exactly where the pointer is located. But in practice, it is not deterministic at all. Because if you have any uncertainty, even at the level of the size of a single atom, of where this pointer is, then every time you apply the law, that uncertainty will double. And after a relatively small number of steps, the error will have grown to 2 to the power n times the initial error. In fact, just 12, 15 applications takes you down from atomic size up to the size of a pool table or something like that. So you get very rapid amplification of small uncertainties. So this little universe is deterministic in principle, but not in practice. So you're thinking, you know, like some commentators have, so how can we know anything? You know, how can we know anything if we have this type of chaotic behavior? In this room, there are individual molecules bouncing around and off each other. And this is what Maxwell had studied and taught us. And their motions are chaotic. When they hit one another and rebound, their uncertainty is not just doubled, it's increased by a factor of 500 or so. So you might think, how could we know anything about the motion of the molecules of gas in this room? But back in school, you learnt things like Boyle's law. Pressure times volume divided by temperature is a constant when we change things in a room like this. So how is this possible in the presence of all this chaos? And it's possible because chaotic motions can have well-defined averages. So these quantities here, the temperature is just the average speed of the molecules. The pressure is the average force per unit area on the wall. So even though the microscopic motions are chaotically unpredictable, their average behavior is changing slowly and highly predictable. This is an important lesson. There are commentators, Stephen Jay Gould, I think, never understood this. All this stuff about rerunning the film of evolution over again, you get a completely different answer. Not so. On the average, you could get a very, very similar answer, even though microscopically it might be very, very different. So the question you've got to ask is about the average behavior. And some systems have this well-defined average behavior, even in the presence of chaos. The person who, interestingly, first appreciated that this was a right question to ask was Florence Nightingale back in the early 19th century. Florence Nightingale's famous as a nurse, but the reason she was successful as a nurse was because she was a pioneer in the development of many methods in statistics and data analysis and data display. And she was one of the founding fellows of the Royal Statistical Society and became a member of the Order of Merit in the UK, which is the highest sort of honour that academics could hope to achieve. But that was as much for her contributions to statistics as for nursing. But she used the statistics to work out what treatments, what spacing of patients was effective and what things were not, and stopped doing the things that were not and did more of the things that did work. And the question that she asked was that many people, you know, had worked on these theological, natural theological arguments about the appropriateness and the way that nature seemed to be tailor-made for life. You know, that life seemed to fit its environment like a glove. Yes, Darwin would eventually give another explanation for this. But she noted that these instantaneous points, that the fact that our habitat fits us in a tailor-made fashion, is a necessary condition, but it's not sufficient to explain why life persists on Earth. You've got to explain why there is a stable average behavior, why the behavior continues like that with time. So this was her contribution to that debate. And she saw that the idea of stable averages is just as important as of instantaneous points. The thing I think she had mainly in mind was the balance between males and females in the population. Okay, not only do you need the balance to be about 50-50, but you need it to stay like that. Otherwise, you're going to have a disaster. Well, these ideas of chaotic unpredictability, what I mentioned before, how laws can be simple, outcomes can be complicated, give you a way of looking at everything that we try to gain some understanding of. So what I've plotted here are a measure of how uncertain we are about the basic equations or the laws of nature governing certain things, from large scales down to very, very small ones. And here, how uncertain we are about the outcomes or the phenomena that we see in nature. So down here, where we have very little uncertainty about the laws or the phenomena, this is simple chemistry. You know, this is making copper sulfate crystals, simple engineering, things that we've done 1 trillion times over modern history, where both the outcomes and the rules are simple. But if you look up here, when we reach meteorology, turbulence, what happens when you turn the bath tap full on, one of the most complicated things to explain that science faces, we are in situations where we know the laws extremely well. Here's the dynamics of the solar system, surface of Jupiter on the conference slide that you saw at the beginning, the rings of Saturn. We know the laws of gravitation and fluid mechanics that govern these things extremely well. But the sheer complexity of the phenomena overwhelms us. There's so much of this chaotic sensitivity going on that we can't make good predictions. Up here, things that you observe at CERN, all that happens at CERN is that one particle decays into, say, 2 others, or 2 particles hit one another and make 2 others. It's very, very simple phenomena. But we have ignorance of the varieties of particles and of the fundamental laws which are in play. We're trying to find out those laws. So here we have a different sort of ignorance of the unknown, that it's ignorance about the laws. And going further upwards, quantum gravity, trying to understand black holes, the origins of the universe, again, we're facing a phenomena that is not as complicated as the weather. But our ignorance of the laws and the complexity of the laws is much greater. Over here, we have different sorts of things where uncertainty about the laws that are in play and the phenomena are growing. And up here, we have many of the things that are studied at this institution. These sit far up here because they're qualitatively different. They have a type of self-interacting complexity, okay, in that if I try to predict the weather, it doesn't change the weather. But if I go on television and I predict what's going to happen to the economy or what's going to happen in a future Brexit referendum, if there is one, it will change the course of that referendum. And there is no logical way in which you can make a public prediction of that sort which will incorporate all the consequences and the impacts of your prediction on the voters or the listeners. If you keep it private, you can know exactly what people are going to do. You can know what their actions are going to be in the future. But if you announce it, if you tell them what their future actions are going to be, they can always act in such a way to falsify what you're going to do. There was, I fear, a great body of totally incorrect work by Herbert Simon called something like the bandwagon effect that claimed sort of the contrary to this. But I think eventually it was sort of nailed down that there was an illegal use here of the Brouwer fixed point theorem, and none of the results were true. So on this sort of middle ground here, this dotted line, above it really we have very incomplete knowledge of many things. Below it we have pretty good knowledge of many things. So the dotted line is supposed to go through turbulence and there'll be long climate change sitting down the end there. But there is an interesting region where chaotic unpredictability somehow seems to merge with order and symmetry. And it's become called criticality or critical phenomena. So the paradigm is to have a pile of sand, better to have a pile of rice, and you let little grains tumble down onto a flat surface. And you can try it yourself, see what happens. You build up a pile, a heap, and it gets steeper and steeper, but it doesn't keep getting steeper forever. eventually it reaches a critical steepness, and then it gets no steeper. And it maintains that stable steepness by avalanches of sand occurring. And if the sand is nice and smooth and doesn't stick together, you will be in a situation where there are avalanches of all sizes, from 1 or 2 grains to occasionally the size of the whole of the side of the heap. And in that way, there is a control over the steepness that extends over the whole slope of the sand dune. And this is sometimes called self-organizing criticality. Self-organizing, you can see, because somehow this process, which is a whole lot of random, in fact chaotic, trajectories of sand grains. If you change a trajectory very slightly, it'll have a different history. It'll fall down the other side of the dune. So that's why it's self-organizing. It's critical because at any moment it's on the verge of instability. So the avalanches, the instabilities, are here maintaining an overall order. There are many structures in nature like this, and I always like, this is my sort of unofficial sort of picture, a sort of theory of the things that we like in the world of art and music and drama. You know, so to be controversial, you know, what's good art? What's a good play? What's a good book? One good test is, do you want to read it again? Do you want to go and see it again? Do you want to listen to it again? And the things that seem greatly appreciated, whether it's Shakespearean plays or great pieces of classical music or even modern music, they have the property that you do want to go and see them again. You do want to listen to them again, because small changes in the way that they're performed, different directors, different cast, different musicians, produces for you another completely different experience. So in some ways, great works of art and literature and music have this type of sand dune type of structure, that when you make small changes to the way they're presented to you, you have a whole new experience. The banal does not. Okay, so you can see, you know, Terminator 36 once, but I suspect you won't want to see Terminator 36 twice, let alone 36 times. So we like a certain type of sensitivity to small changes. We wouldn't like it if it was completely chaotic, okay, and bore no relation to when we went to see it before, and we wouldn't like it if it was rigid, like a pyramid at Giza. Not that I have anything against Egyptology. So as we move sort of forward to things that are more well-defined, a little more mathematical, there's a picture here, constructed as you what might call the ocean of truths that mathematicians, computer scientists, or physicists think about. Down here, there are things, practically computable truths. So the things that you can do with this little object here, and bigger versions of it. It's worth reflecting that dramatic pictures like that Mandelbrot set that I showed on the very first title slide, this type of mathematics and the study of chaos was only made possible, really, by the computer revolution that occurred in the 80s and developed further into the 90s. The appearance of small, inexpensive personal computers meant that single individuals could carry out experiments in mathematics with very good graphics, simple programming, easy to change conditions, and they could look at the results. In decades before that, there were computers, but they were run by ferocious large research groups of hundreds of people, and they were focused on blockbusting problems like making bombs, predicting the weather, exploding stars, and so on. But the personal computer put computers in the hands of single individuals And they created a new science, a science of experimental mathematics that could study problems that could not be solved exactly with pencil and paper, certainly not with pencil and paper in 30 minutes under examination conditions. So the whole of our education process and the development of mathematical science had been biased towards problems that admitted small, simple solutions. They had a lot of symmetry. They were, if you like, easy problems. So now you could start to look at problems that in some sense are hard. And we'll see what sense in a moment. So there are these practically computable problems. There are other problems that if you had a computer that would run forever or for a trillion years, you would be able to access. So there are truths of mathematics that a computer could find in thousands of years. The whole development of modern encryption, the thing that keeps your credit card secure, is based on the fact that some of those computable truths, which are not practically computable, are very, very simple. So, for example, if you have two enormous prime numbers, 60, 70 digits in length, and someone multiplies them together and hands you the product, 130, 140 digits long, and you have to find the two factors, the two prime numbers that were multiplied together to make the product, this will take you many thousands of years using the world's fastest computer. So the encryption of your credit card details when you put it in the hole in the wall is based on the fact that no one is going to be able to find that factorization in any useful period of time. If some mathematician somewhere in the world did find a fast algorithm to factorize products of enormous primes, the world would be in a very serious situation. All commercial, military, and diplomatic codes would be broken. And of course, if somebody has found such a fast factoring algorithm, they wouldn't tell you or anybody else. So that's the things that are computable but take a very, very long time. There are then things that mathematicians call decidable true. So things where you might be given a statement and you can determine whether it is true or whether it is false. So if somebody shows you a chessboard with a configuration of pieces on it, can you deduce whether that configuration is a valid chessboard? So can you have reached that from the starting positions of all the pieces? Not such an easy question to answer. So as a counterpart for any system that has starting positions and rules, axioms and rules of deduction. But the remarkable discovery of Gödel was that beyond that, there are mathematical truths that cannot be decided. Okay, so we're going to sort of delve a little into some of the pieces in this picture. So the first, tractability, like the practical computer problem. Easy problems are problems, there are n parts to the problem. It's like Don Trump's tax returns. So I heard on the news yesterday, he's got 600 or something companies, and they're only the ones he knows that they know about. So if you have to do a tax return for all the details of 600 companies, this is an easy problem in the sense that the calculation grows in proportion to the number of companies that you're operating. Okay. But a hard problem would be if each time you add another ingredient to the problem, the computation time doubles. And if it was 600 companies in that situation, you'd never be able to answer the question. So there are some problems that have this property, that each time you add another bit to them, the computation time to get to your answer doubles. And chaotic systems are like that. So you remember the arrow moving around the circumference of the circle, a doubling of the angle, the uncertainty grows by 2 to the power n after n moves. So this is one of these problems, okay? So there are rather mundane situations. I came across one recently. So sometimes I sort of involved in doing things to do with maths and sport. If you're interested, you'll find I've written a book on this. And there's a seemingly mundane problem that some Dutch mathematicians are also interested in. We were at a meeting last year about it with Steve Brams here from NYU. And they wanted to be able to predict from a particular time in the soccer season in Holland and Norway, by looking at the games played and the games still to play for the rest of the season, could you predict, or at what stage could you predict, who was going to be promoted and relegated? Okay. The journalists do this in a very simple way. They just say, what's the maximum number of points that some team could get? And if it's not enough to avoid relegation, they're relegated. But if you think you could take into account the fact that all the teams are playing some of the other teams, there's more information available. And it turned out that from a particular point in the season, if you gave 2 points for a win, 1 for a draw and none for a loss, which is what used to happen in league soccer in Europe, then the situation became predictable to the future. It was an easy problem. But if you use the modern system where you get 3 points for a win, 1 for a draw and none for a loss, it was not. So why would that be? Well, you can see that under this system, each game just dispenses 2 points. So if somebody wins, somebody loses, one gets 2 and the other gets 0. If they draw, they each get 1. But in this system, if somebody wins, they get 3 points, the other gets 0, so 3 points given away. But if they draw, you just give away 2 points. So each game has 2 possibilities for dispensing the points. And this produces this doubling effect in the whole computation and makes it intractable. Well, what about undecidability? So this is sort of something hard at some level. Here's Kurt Gödel, who lived down the road in Princeton at the Institute for Advanced Study. So Rebecca Goldstein, had she been here, could have told you lots about him. She wrote a book about him. But what he did, which nobody was expecting, 1930, Hilbert had thought that it would be possible to prove that any problem that you formulated in mathematics or in arithmetic could be decided. It could be determined whether it's true or whether it's false. So, because he thought you just have these axioms of arithmetic and you just turn the handle and you look at all the deductions. It's like a great web spreading out in front of you, all the truths of mathematics, and you should be able to determine whether a statement that someone gives you sits in that web or not. He was confident of that because he'd proved that this was the case for geometry, Euclid's geometry. So if somebody gives you a statement of Euclidean geometry about triangles or points and lines, it is possible, after an enormously long deductive process that you could tell a computer about, to determine whether that statement is true or false, whether it follows from the laws of geometry. And he thought that, well, just add a few more axioms, we make geometry a bit more powerful, we turn it into arithmetic, same sort of result is going to occur. But he was shocked when Gödel announced at a small conference that he proved the opposite. That in fact, if you have a system that's got a finite number of axioms, it's not good to have an infinite number because then any statement that you care to choose under the sun could be one of the axioms. And if it's big enough to include arithmetic, complicated enough to include arithmetic, and if it's consistent, so that is you can't prove that 0 is equal to 1, then there are statements of arithmetic which you can neither show to be true nor false using the rules and axioms of arithmetic. So it's not as Hilbert imagined, okay, that the world of the truths of arithmetic are much bigger than this smaller world of the decidable truths. So I call this mathematical jujitsu. You're sort of using mathematics to prove something that it can't do. Say a few intuitive things about this. How does it work? Okay, so if you like mathematics, you can sort of stay awake, but if you don't, go to sleep. That what Gödel did, in a simple way, was to set up a correspondence between statements of mathematics and statements about mathematics. And he did that by making use of the fact that arithmetic has something called prime factorization. So you can take any number and you can express it as powers of prime numbers in one and only one way. So 9 is 3 squared, okay? 12 is 2 times 2 times 3. So here's a harder one. 9,000 is 2 to the power 3 times 3 squared times 5 cubed. And he took the indices there of the first 3 of the prime numbers. Some of them might be 0. There's no 7, for example. This Gödel number is 323, the yellow ones. So if you have a really big one like this, its Gödel number is 656. And then what he did with these numbers here was to make each one of them equivalent to some aspect of a logical statement. So 6 might be replacing 0, 5 might mean equals, and then the number 656 corresponds to the statement that 0 equals 0. It's a rather trivial statement. But this is a general idea of how you get a correspondence between mathematics and statements about mathematics. And then all he's doing, he thinks about this statement. The theorem having Gödel number x is undecidable. And he inserts for x the Gödel number of this statement. And then he has effectively the proof of his theorem. And there are simple examples like this that are known nowadays. Take 6 or more 3x3 matrices with whole number entries, and you multiply them together in sequence. Can they be multiplied in such a way that you get the answer 0? And we don't know, because we can't know, because it's been proved that this problem is undecidable. It's known as the mortal matrix problem, if you want to follow up on the web. What's going on here, there is another aspect to this. Why is geometry decidable? The key here is you've got to have a complexity at least as deep as arithmetic, because arithmetic has this prime factorization. So you have a way of uniquely identifying numbers by this prime decomposition. If you had geometry, geometry doesn't have numbers in it. It has lines and points. And every point's the same as every other point. And every line's the same as every other line. So you can't have a sort of mapping between points and statements about points and lines and statements about lines, because you don't have this unique way of identifying the points and the lines. So this is why this type of result comes in when you get a level of complexity that's at least as bad as arithmetic. Greg Triton will say something about this tomorrow. He has a nice alternative way of looking at this that Andrei Kolmogorov in the Soviet Union also developed, and you can use it to produce all sorts of other sort of undecidability, unknowability results. And one of the things that you can do is a helpful way to look at this, that if you have a sequence of symbols, suppose they're zeros and ones, the top one, if it goes on like this forever, is ordered, I hope you recognize. The one below, not obviously so. What do we mean when we say that something is ordered or non-random? Well, we're thinking that if we wanted to tell our friends in Australia what this sequence said, and it was millions of entries long, we wouldn't have to send them the whole list. We'd just send them a rule that 1 follows 0 and 0 follows 1. And that rule is much shorter than the listing of the whole sequence. And so for something to be ordered, all we mean is that we can re-express it as a formula or a program or a rule that's shorter than the listing of the sequence. For a random sequence, this is not possible. There is no compression. We cannot re-express it as a formula that is shorter than the listing of the sequence itself. Now, what Kolmogorov and Chaitin exploit, the fact, is that you can obviously show that something is ordered. You just exhibit the compression, the rule that abbreviates it. But you can never prove that something is random. So you can never say whether a particular sequence, an unending sequence, is random, because you'll never know that there isn't some theorem, some mathematical truth, which, if you had it to hand, would be able to provide the compression. And Gödel has told you that there are undecidable truths, and one of those might be the one that compresses the sequence. So this is the connection between randomness and order, Gödel undecidability, and you're going to hear some more about that from Greg tomorrow. So it's a rather unexpected and sort of deep connection between things that appear to be very, very different. But when you look at them in the right way, they're not. There's another final look at these sorts of things that I like. John Myhill was an American philosopher and logician, also a very fine musician. He was professor of music as well as logic at his university. And he produced this sort of metaphorical way, he liked to talk about it, of distinguishing features of the world. So computable properties are properties where there's a definite process, like a program machine, that can determine whether if somebody gave you an example of something, whether it has this property or it doesn't. Okay? So obviously being a prime number is one of these. Being an even number is a trivial one. There are other properties which are listable, so that there is a program which can list all the examples that possess this property. And it may take an infinite time to complete this list. But there isn't a program that can list all the things that have not got that property. It might be all the varieties of banana I mentioned at the beginning. But you can see there, everything that's not a banana, okay, can be really a rather big deal. But there's another collection of things that he calls prospective properties, and these are neither listable nor computable. And I think these contain lots of the interesting things about the world. I mean, they contain being a true statement of arithmetic, because of Gödel, but they contain things like beauty, ugliness, simplicity, truth. These things can't be recognized or generated in finite deductive steps, and nor can the examples that don't have those properties. So I think this recognition earned me a $1 million grant once when the referees' reports came back and demanded that there be more metrics to evaluate the effectiveness of a particular education program. So I argue that what we were testing were in effect prospective properties. There is no metric. You can invent one by simplifying beauty by saying, well, if there are 4 corners to the shapes you're generating, we'll say that's got high beauty. If there's only 3 corners, it's lower. So what people do is to replace these prospective properties by some selection of features from the things in view. So that's Myhill's. I always find this a rather sort of insightful, simple approach. I should say something about arrow impossibility. This is about voting. Unfortunately, the British members of Parliament that are engaged in the so-called indicative votes have very little understanding, and the Speaker of the House of Commons seems to have zero understanding of that there is a well-defined theory of how you create a sequence of votes in order to come to a definite conclusion. But they just seem to sort of think up whatever they want. So people spend their lives solving situations like that, but they don't seem to be aware of that. And what Ken Arrow proved and got the Nobel Prize for is that there is no voting system, no rank ordering system, that tells you who comes first, second, third, and so on, with at least 3 candidates that has the property that if it's democratic, first of all. So if every voter prefers X to Y, then the whole group prefers X to Y. Okay. At the bottom, there's no dictator. So there's no single voter who always determines what's going to happen, regardless how everybody else votes. Okay? So these are features you would like in a system. In between, there's something else that you would like, that if every voter's preference between 2 candidates is unchanged, then the group vote shouldn't change. Okay, it seems sort of obvious. There's a little story here about that, it's probably apocryphal, the philosopher who goes to a restaurant and the waitress comes around and tells him and all the other ladies and gentlemen in the party, the other philosophers from the university, that they have either beef or fish. What would he like? So he says, I would like beef. So the waitress goes away, and a few minutes later she comes back and she says, there's another item on the menu. There's chicken. Does anyone want to change their order? And that first philosopher said, yes, I'd like to change from beef to fish. So this is number 2. So this is the irrelevant alternatives. And it arises, my daughter was an ice skater and she's a professional ice skating coach now. So I sort of know more than I should know about ice skating judging systems. So if you want weird voting, you want ice skating CSA 2002. Because the way international judging was done in ice skating was an attempt to violate Arrow's theorem. And finally, at the Olympics in 2002, it all sort of came crashing down. And after that, they had to change the judging system. So what happened, here are some names you probably recognize, Kwan, Hughes, Cohen, Slutskaya. And they do a short program, they do a long program. And you remember all those 6.0s and 5.9s, all those marks that the commentators get so excited about and people scream about. They're all thrown away. They don't get kept. All that gets kept is the rank of the skater at the end of the program. So for the short program, they get half a mark for being the first, 1 for being second, 1.5 for being third, 2 for being fourth. So it doesn't care what all the marks were. All they're keeping were the ordering, the ranks. When they skate the long program, they double these numbers because it's the long program. So being the best long program, you get 1. The next best, you get 2. And next best, you get 3. And then they add them together. So the smallest score, smallest rank, would be the winner or the leader. You mustn't do this, Arrow's theorem. You mustn't add ranks. So before the last competitor skates, this is the situation. Kwan is winning, 2.5. Hughes is next, 3. Cohen, 4.5. And then Slutskaya is waiting to skate. So what happens is that she's the second best in the long program. So the ranks shuffle. Hughes is 1, Slutskaya 2, Kwan 3, 4. You add them up. These two are now tied in the lead. You break the tie by best long program, so Hughes wins. But the point is that Slutskaya's performance has altered the relative positions of Kwan and Hughes. It's like the man ordering the chicken. Okay? So why has Slutskaya's performance altered the relative merits of Hughes and Kwan? So it's because what's going on here is that you were adding ranks, and you mustn't do that. What you should have done all along was kept all the scores and added them together, and then you wouldn't run into this paradox. And that's basically what happens in ice skating now. Scores are divided to particular attributes. Okay, last few slides, I want to say something about cosmology. It's what I work on most of the time. There are very, very different types of unknowability in cosmology. Cosmology is not like other sciences. You can't experiment on the universe. You have to take what's on offer. Okay, what do you do because you can't experiment? You look for correlations. So if your theory says that all big galaxies are red in color, you look at many galaxies as you can, and you see if there is indeed a correlation between red galaxies and their mass or their size. So you look for correlations as you would as an experimenter. Unfortunately, Popper, philosophy of science, doesn't help very much at all. People in my sort of subjects don't take Popper very seriously at all. I never did, even when I was at school. The trouble is, he thinks that all experiments are correct and all theories are wrong. So he never seems to occur to him that some experiments are wrong. So if you make a theoretical prediction and you carry out an experiment, the fact that the prediction experiment is not borne out, or the prediction theory is not borne out by the experiment, could be due to an error in the experiment, it could be due to a bias in the experiment, or it could be because the theory is wrong. All experiments ever do is to change the likelihood that a theory is true. They can never rule it out, they can never falsify anything, they can never confirm anything, as Popper said. But in astronomy and cosmology, the real reason Popper's not very helpful is because there are selection effects, there are biases, and you cannot change them. So if, for example, you create a great catalogue of the brightnesses of all galaxies, so you want to see whether very bright galaxies are commoner than very faint ones and so on. So what's the spectrum of brightnesses? Then, of course, bright galaxies will be overrepresented in this survey because they are easier to see. So making predictions, carrying out observational tests of them, is not as simple as the sort of textbook version of Popper falsifiability. We, of course, in cosmology also only observe the past, because light takes a finite time to reach us, and we have to deal with intrinsically random processes. Here's a sort of schematic picture of the expansion of the universe from its early stages to its present extent of a visible universe of about 42 billion light years. Started accelerating about 4 or 5 billion years ago, rather unexpectedly to cosmologists. But what are the awkward problems? The fact the speed of light is finite means we don't have access to the whole universe, which may be infinite. So there is something that we might call the universe with a capital U, and there is something called the visible universe, which we could see with a perfect telescope. But the two are not the same. So we're always limited to a finite fraction of the whole universe. There are also selection effects. I just mentioned now this one, say, about the brightness of galaxies. But if you have a universe that is very, very different from place to place, you even have different universe, see in a moment, then what can happen is that you might be able to predict what the probability is of the universe having a particular attribute. But what does that mean? If the probability was low, what would that mean? That you wouldn't expect to see it, that you should rule the theory out if it doesn't agree with what we see, because we find that very often an attribute, it might be the value of a constant of nature, has to fall within quite a narrow band for life or complexity of any sort to be possible in the universe. So as observers, we would have to be in this little narrow band possibilities, regardless of how improbable it is. But really our dilemma is we don't know how to calculate or predict the probability of anything. in astronomy and cosmology. We don't know the a priori probability distributions that emerge from the apparent beginning of the universe. This has become a major problem because people now have to face the fact that we expect our universe to be wildly different in structure if we could view it far enough beyond that visibility horizon. So the visible universe that we see is the expanded image of a tiny fluctuation, small enough for light signals to pass across it in the first instance of the expansion. But beyond it, like the expansion of a foam of bubbles, there will be other regions that expanded in different ways and have very different structure, perhaps even different aspects of physics. So what we need to know is the probability distribution of the outcomes in this structure. We also now alarmingly realize that this process continues in time. So not only is geography a more complicated subject than when you were at school, but history is as well. And we're in a little fluctuation that underwent this inflation. Subregions of it will undergo further inflation, subregions of them further inflation, and so on ad infinitum. So again, this probability problem arises. How do we work out the probability distribution, the probability measure for the outcomes in this type of multiverse structure? So far, nobody knows how to do that. Finally, a very deep problem for the future, doesn't worry us, but I said that we discovered that the universe is accelerating. And this has been happening for a few billion years. But the fact that the universe is accelerating means that in the far, far future, that should be 100 billion years, if there are any astronomers about, it won't be possible to do cosmology and astronomy anymore. Why is that? Well, the acceleration of the universe creates a horizon rather like a black hole horizon. It's fixed. It doesn't keep getting bigger day by day. So gradually, all the stars and distant galaxies that we can see pass out through that surface. And after they do, they're never seen again from the Earth or whatever's here at this position. So eventually, after 100 billion years, all the other galaxies that we see in the universe today will cease to be visible from here. They will have passed out through that one-way surface. And if you're an astronomer at that time, you won't even be able to determine that there are other galaxies or that the universe is accelerating or expanding in the way that we can study today. So not only is the modern period, the last few billion years, conducive for the evolution of life, up until this time, it's also rather conducive for the study of the universe. So after 100 billion years, you won't be able to learn the sorts of things that you can learn today about the universe. If you want to do cosmology, you want to know about distant galaxies, you'll have to do it like Professor Scott. You'll have to look at old books. You'll have to look at journals. You'll have to see what people wrote in the past about the study of astronomy. It will become a part of history. So the history of science will become the replacement for this sort of science. So there is a period of cosmic history during which it's possible to study and understand the universe and know about it in a very, very broad way. But that doesn't continue forever. Information processing will effectively stop. Things will be very, very far away, very, very far apart. If there are life forms around at that time, they won't tend to be astronomers. They'll probably be historians of astronomy. So I hope on that downbeat note, I can come to an end, and I hope I've given you some quick view of some of the aspects of the unknown and the limits of science, which it's proper to regard positively. So these limits tell us new and profound things about the structure of the universe, about the nature of mathematics, about the nature of physics, about the nature of sensitive and chaotic systems. So they're not just examples of negativism. They are positive contributors to shaping the boundary of certain sorts of knowledge. And traditionally, laws of nature, constraints on what is possible, has also told us what is possible. Thank you.
I'm going to come and sit there. My microphone's on. Well, thank you for that tour de force. As you said, you know more than you should do about rather a lot of things. I'm sure many people here know Isaiah Berlin's story about the hedgehog and the fox. John is clearly both a hedgehog and a fox. He knows an awful lot about a few things, and I mean an awful lot about one thing and an awful lot about many things at the same time. John, we've got very little time now. We're down to 5 minutes. I'm going to ask make one very quick comment. I think your talk was a very interesting foil in a way for the first session. Michael Scott said that what's interesting is we know much more about the future than we do about the past. You were basically concerned entirely with the future. You were interested in predictability. When you talk about knowing, you know, what can we predict is coming down the road to us. And you weren't concerned really with what we know about what is true at present or what has been true in the past. Even to take your opening example of the rigid beam, of course we can't predict in advance what the forces will be, but we could know by putting balances under the beam exactly what they are. And the same is true right the way, I think, right up to your examples of unknowable truths of mathematics and Gödel's theorem. Your matrix problem, mortal matrix problem, could be shown to be true, that you can multiply the matrices to produce that answer. You just can't predict whether it's going to be true, but anyone who actually discovered they'd done it would, of course, have then proved that that is a truth which is and was and had become knowable. Now, it's well, there's not. We could go on a lot. We could obviously go on that theme in many ways, but I actually I'm not even going to take the time to develop that now because we have time for about 2 or 3 questions.
I got one comment,
yes,
and that is, so what you say about the focus on the future and prediction is true about the first collection of examples. Oddly, it's not true about the cosmology, because of this feature that light takes a finite time to reach us. All that we know about the universe is as it was in the past.
Yes.
So we know almost nothing about the large-scale structure of the universe today. We know what it was like 10 billion years ago, or 2 billion years ago. And in some cases, we can see structures in the universe that are heading for other structures. And we can measure the speed from the Doppler shifting of the light. And we know that the structures that we're seeing are not there now anymore. You know, they've collided and dispersed. So we're seeing them when they existed in the past, but they're not there anymore. So when people say, how can you know what the universe was like 10 billion years ago? The answer really is, that's the easy part. What we can't know is what it's like today, because we have to wait for the light to reach us. That news is en route.
Right. Yes, but thinking about this general question about prediction or knowing what's true, the Encyclopedia Britannica contains an awful lot of knowledge, but not a single prediction, I would guess. So, but let's take some questions from the audience. The light's so bright in my eyes I can hardly see you. We've got one there and one there. You start, sir.
Yes. This is Prabhakaran, an alumnus of the New School. I publish an online monthly called the East-West Inquirer. I also write books that nobody reads. To shamelessly plug in my latest book, it is an Indian goes around the world, what I learned from my 30-day European odyssey. I'm sorry, I have to plug it in. My question, sir, it's a very simple one from a layman's point of view, which is what I am. Thank you for explaining in simple terms such an esoteric topic, which is otherwise esoteric. And also thank you for bringing the knowledge of Donald Trump. What you said is absolutely right. Every time he adds a new element, he's making it more unknowable. I can add one more. He's making himself more stupid and adding one more lie to the tons he has already said. Having said that, I come to my question. I'm sorry. It's a very simple one. I know what is unknown. I also know what is unknown to me is well known to the rest of the world. And what is unknown to me today will become well known tomorrow. Is there anything that is unknowable? Or when you say it is unknowable, are you not discouraging an inquisitive mind from trying to know that? Is it not the way in history certain sections of society was prevented from learning things? They were told it is unknowable to you.
So the thing about Gödel's theorem is that it isn't just an existence theorem, that there exist statements that you can't prove true or false, but there are examples. Okay, so there are specific conjectures that you can show can't be decided. It was always a possibility that Fermat's last theorem was undecidable. Okay, Wiles produced a proof of it, but it was possible for it to be undecidable. You can have configurations of something like the game of life or of chess, and you could ask the question, is it possible for this configuration of the pieces on the board of Conway's game of life to be reached from the starting configuration? And under some constraints, it's possible that Conway's life game is the same as arithmetic. It's somehow equivalent in information content to arithmetic. So there would be configurations of the game of life which cannot be reached from any previous configuration. And they're usually called Garden of Eden configurations. So in these and other examples, you can give specific statements of questions that you can't answer using the rules and axioms of arithmetic. How you should interpret this is not some mysterious ignorance about the universe or unknowability, but just systems of axioms have certain power. They have certain capability. And there are certain questions you can frame that those axioms do not have the information content that's necessary to reach and answer them. So you could add some extra axioms, and then you would be able to answer the question that you first posed. But you would generate new undecidable questions. So this is a way that the Chaitang-Kolmogorov approach sort of leads you to think along, that there's a certain information content in systems of axioms.
We should wind up on that question.
Okay.
I
hope
I'm
that's
sorry,
enough.
I mean, there's obviously a lot more to say, but I think we should have at least one more question.
Sure, thank you. I appreciate that. My name is Josh. I'm studying cognitive science in education. And one of the things that we often talk about is what kinds of things can psychology or neuroscience add to our ability to do education? And I think that this speaks actually to both of your expertises in my asking, can the mind understand itself? People talk about singularity. People talk about all kinds of possibilities. So I would challenge you to predict: is such a thing possible?
Well, I'm going to talk a bit more about that tomorrow. So perhaps we should leave that one. Is there one more question?
Thank you. My name is David, and I have a question for you that goes back to when I was a sophomore in high school geometry class. So basically, if it's true that most scientists and most cosmologists believe that the Big Bang Theory is the way it happened, and it's true that the universe is expanding at the speed of light or near the speed of light, the question I've been asking all these years is, what is the universe expanding into?
Yeah, it's not expanding into anything. So the universe is everything that there is. If it's infinite, you can see obviously there's no outside, there's nothing for it to expand into. If it's finite, you tend to have an intuition that sort of thinks that finite things are flat, they're two-dimensional like this piece of paper, so there must be an edge. But if a two-dimensional thing was like the surface of a ball, then you could walk around on the surface of that ball and you'd never fall off the edge. And if you inflated the ball, the surface would get bigger. Any point on the surface you stood on, you would see all the other points moving away from that point as though it was at the center. So there's no center and there's no edge. the universe isn't expanding into anything.
So that's different
Don,
than
the universe may not be, but this session is expanding into something, and it's, and I'm afraid
So
that we really have to wind it up because they have to close the hall down, and there are other events coming next. So many, many thanks for that wonderful talk.
Okay.